Hello, this is Jack Jackson. In this video, we're going to be estimating the graph of the derivative function. So the way this GeoGebra app works is we have a graph of a function here, which you can enter in any function you want. So you might experiment with this with various different functions. And we have 10 points here that can be freely moved anywhere around. And the idea is to place those points in places such that they're at the values of the derivative. If we do it correctly, we can click on derivative function and the graph should go through all of the green points. So if we start here, let's see, it might be useful to find the places where the derivative is 0 first. So the derivative is 0 right there. So that looks like about at -9. So somewhere around that vicinity, we should have it going through the x-axis, and there's another one right about here where the derivative should be 0, and then let's do one here as well. That's going to be about here. So those max and minimum values occur when the derivative is 0. So we have those points where we want. Over here we got some negative derivatives. And here the derivative is positive, and here, and you don't have to have these in any particular order. This one was supposed to be 0, and we got some negatives here and positives there. Let's see, let's maybe put a couple like that. Okay, so now we're how high up? I know these are negative. These are, its slopes going down from left to right, so it's negative here, positive over here. But how high do I make it? Well, we have to estimate the slope there. Now we can do this a couple of different ways. One way we can do it is by using symmetric difference quotients. So for example, here at -5, if we go to the left, say the left one, then we're up here at about 5, well, maybe more, maybe higher, 5 point something, and then we go to the right one, it's about, say, -4, so that's a drop of about 9. So that means the graph, the derivative is around -9-ish, somewhere in there. And we could do this for different points. It's dropping even faster here, so it's going to be even lower. Notice that this part of the graph is concave up, so the derivative should be increasing here. Now another way we could do it is we could look here at the tangent line segments that I've got drawn for each of these. And the amount of drop from here to here is the derivative, is the value of the derivative, because these little tangent line segments are going to the right one. So if you look, this drops, let's see here, let's say right here, it's going to drop 1, 2, 3, 4, 5, 6. Let's see. 1, 2, 3, 4. 7 point something. Okay, and this one is less. So I think I got this one too low. It's dropping here only about, let's see if we go right here, it's dropping, how much is that? That's 1, 2, about 3. So that should be around -3, somewhere in that vicinity. How about this one? Well, this is going up, so this should be positive. How much? Well, right in here, it's going up, about 2 units. That's going to be about at 2. Over here, say right in here, it's going up about 1.5 units. So in here, we're looking at about 1.5 or so. There, we're not quite at the maximum. Let's see if I can get that where it's horizontal. There's at 0. This one should be where it's horizontal there. This one should be where it's horizontal, looks like about there. Let's see, pause, this going up, let's see, concave up here, so increasing. Somewhere in here there's an inflection point, it maxes out, it comes back down because it's concave down. But from here over to here, the function is increasing, so that's all positive numbers here. Function is decreasing here and negative numbers here. Okay, let's see if we can get these guys. I think I got that one in the vicinity, and maybe here. How far down? Let's put it in here. How far down does that go? That's dropping about more than 2, so negative 2 point something there. That's at 0, and somewhere, let's put it, let's say in here, how far is that going up? Well, it's going up about 1, 2, 3, 4, 5, 6, 7, about 8. So this is going to be in the vicinity of 8 there for Y. Well, let's see how I did. Pretty close. I was a little low on that one, and a little low on that one. Okay, but otherwise, and just a little bit low there too. But not bad. Not bad overall. That's where we've got it. So if I take a little bit more time, perhaps I use symmetric difference quotients as well as looking at those little tangent line segments, I could have gotten a little bit better graph. So the idea is to use what you know about the shape of the graph and where its derivative would be to help get it in the right vicinity, and then fine-tune it a little bit with actually looking at the actual value there by approximating it from the either by looking at those tangent line segments or looking at symmetric difference quotients. And so that's what we get for the derivative function. And you can practice this a little bit and get better and better at estimating points of the derivative and making sure you at least know what the basic shape is going to be. So even without graphing it, I should have known that, for example, this part from here down to this minimum, the function is decreasing, so that's negative values. The graph of the derivative is going to be below the x-axis. It crosses the x-axis right here where this reaches a minimum. Looks like it's around -9, thereabouts. And then the original function is increased from there over to here, which makes the derivative positive. So that's going to be positive over in this part. It's somewhere it switches from concave up to concave down, and that's going to happen at an inflection point on the original graph, which is at a maximum here on the derivative, somewhere around there. And then what happens from there? Then the derivative starts coming back down, but it's still positive until where? Until it hits this maximum, which is where the graph crosses the x-axis, the graph of the derivative. Maximum has a horizontal tangent line. Maximum on the original function, or minimum on the original function, has a horizontal tangent line, which has a slope of 0, so the derivative is 0 at those points. So the graph of the derivative crosses the x-axis every time the original function there is at a max or min. And then so forth. From here over, the original function is decreasing from here to here, so that means negative values for the derivative. And again, it switched from concave down to concave up, so there's a minimum right there somewhere at the same place that this has the same x value that the original function has an inflection point. And then we're still negative, so the function is still the original function is still decreasing, so the derivative is still negative till it hits this minimum. And from there on up, the original function is increasing concave up, so the derivative is positive and increasing. In other words, above the x-axis and going up. And just change this to just some different formulas just by typing in this box. Experiment with this to get a little practice, and you can get better and better at solidifying your understanding of what the graph, estimating points on the derivative from the graph, and then also making sure you're reinforcing your ideas of the relationship between the graph of the function and it's the graph of its derivative function. Hopefully that will help you out a bit. Till the next video. Bye-bye.